Welcome, everyone. For today's prep, we're going to be looking at the idea of Riemann sums. And, well, we're kind of getting to the end of this is our last prep video. And this idea is going to lead us to the definition for what the definite integral actually is. So we've seen kind of how to calculate the definite integral using antiderivatives and all of that. But here we're going to actually see what the definite integral actually is. And the idea comes down to these Riemann sums. So there's two ways to approach Riemann sums, kind of naturally. You can do it by considering the distance problem, where you're trying to figure out how far a object travels if you know its speed and how long it's traveling for. If we have time, we'll look at that example. But for today's prep, we're going to look at the area problem. And this is something we've been doing. We've seen how we can use the definite integral to help us calculate the area under the curve. So we're going to pretend that we don't know that yet. And we're going to kind of get to, by trying to figure out the area here, we're going to get to our definition of the actual definite integral. All right, so the area problem. If we're looking at a section of the x-axis and we want to figure out the area under the curve, well, we're going to try to estimate it. And the idea here is that if our curve was constant, then we're looking at a horizontal line. And that means the area underneath that horizontal line is going to be a rectangle. And we actually know how to figure out the area of a rectangle. It's just the height of the rectangle times the width. Well, for most of the interesting curves we're looking at, our curve is not constant. There's some curve to it. So the idea is we're going to take our section of the x-axis, our interval from the x-axis, and we're going to slice it up into a whole bunch of little pieces, which we call subintervals. So we're going to split up our main interval into a whole bunch of tiny little subintervals. And because these subintervals are going to be so small, the height of our curve over each of those subintervals we can assume to be constant. So we're going to take our region that sits under the curve and we're going to break it apart essentially into a whole bunch of tiny little approximating rectangles. And once we find the area for each of those rectangles, we're going to add them all together to get our estimate for the total area under the curve. So let's try a little example. So we're going to use some given approximating rectangles to estimate the area under the graph of y equals f of x over the interval from 1 to 7. So let's look at this graph here. So we've got our curve, and we're interested in figuring out the area under the curve starting at x equals 1 and then ending at x equals 7. So we're trying to figure out this area for this region. All right, so the idea, as we mentioned, is we're going to break this region apart into smaller pieces, and we're going to use rectangles for those smaller pieces. So we've got our section of the x-axis going from 1 to 7, and the idea is we're going to slice this up, and from each of these subintervals, we're going to get a rectangle. So you can tell this is an estimate because, there's pieces of our region that we're not hitting, our rectangles don't cover up, and then there's kind of excess regions here where we're covering up part of our XY plane that's not underneath the curve. So we kind of are missing pieces, and then we have kind of excess pieces elsewhere. So we are just doing an estimate. So let's go through the calculation. All right, so let's call this first rectangle, excuse me, we'll call this R1, rectangle 1. So let's figure out the area for that rectangle. So we want the area of rectangle 1. Well, we need two things. We need to know the height and we need to know the width. All right, so if we look at our x-axis here, we can see that the width, we're going from 1, then we've got 2, and then we've got 3. So the width of this rectangle is 2. So in general, it's going to be height times width for that first rectangle. And the way we've done this, the width we know is 2. All right, so what's the height of this rectangle? Well, we're using this point along our curve as our height, giving us information about our height. So the height here we can extract from the y-coordinate. So what we're seeing in this first rectangle, the height is 1.6, and then the width of the rectangle is 2. So again, we're getting the width of our rectangle as the section of our x-axis there, or the length of it. So we're going from 1 to 3. So that's our width. And then the height for this first rectangle is, we're using the y-coordinate of our curve at x equals 2, and the y-coordinate there was 1.6. All right, so we've got our height, we've got our width, and if we multiply those together, we get 3.2. So now we just play this game for the other two rectangles. So we'll figure out the area for rectangle R2, and then we'll figure out the area for rectangle R3. And because these are rectangles, it's always going to be height times width. So if we look at our graph, let's figure out the height for those other two rectangles. So we've got R2, and then we've got R3. So for R2, we're using our x value at 4, and we're using our function value there to get the height of that second rectangle. So that's what this point 2 is. That's the height of our second rectangle. And then for our third rectangle, we're using 2.5. All right. And the way we've done this is we've sliced up our x-axis so that each of these rectangles has the same width. So we can actually figure out the width using some calculations. A lot of times we call the width delta x. And it's really the length of the entire interval, so the length of the entire interval going from 1 to 7, divided by the number of rectangles that we want to use. So in our case, it's 7 minus 1. That's the length of our main interval. And we wanted to use 3 rectangles. So if we calculate this, we get 6 over 3, which is 2. And that's what the width of each of these rectangles is. All right, so going back, we know what the height is for each of our rectangles, and we know what the width is. So now we can calculate. So for rectangle 2, the height is 0.2, and then the width is still 2. And then for R3, our height is 2.5, and the width is still 2. So we've got our heights, and then we've got that width, that common width. All right, so what do we get if we calculate these? Well, we get 0.4, and then we get 5. So now to approximate our area under the graph, we're just going to add these 3 rectangular areas together. So the area under our curve is going to be approximately, we'll say A1 plus A2 plus A3. So A1 is going to be the area from rectangle 1, A2 is going to be the area from rectangle 2, and A3 is going to be the area from rectangle 3. So if we add those together, we get 3.2 plus 0.4 plus 5, which is 8.6. So this 8.6 is giving us an estimate for the total area under the graph. But again, it's an estimate. So there's pieces where we're kind of doing too much and other parts where we're doing too little. So it is just an estimate. Okay. So this type of calculation, though, gets kind of repetitive if we have to write it all out. And so it helps to use what we call sigma notation. So when we're adding repeated things over and over again, a way to shorten it up. So if we had like a bunch of different things that we were adding together, so maybe some number A1 plus some other number A2 plus A3, and we keep going. We have a whole bunch of things that we're trying to add together in this big list. What we can do instead is introduce big sigma here, big sigma notation. And this is just a fancy addition sign. So the way you read this is the I here is an index number, and it's usually a positive integer. So normally some common starting places are either 0 or 1. I equals 1 tells us where this index value starts. So we're starting at I equals 1 here. And then n tells us where the index value ends, and we include this. So when we look at this, we're adding up the list of terms from list of terms here, and we're starting at index 1, and we're adding all the terms going up to index n. So that would look like A1 plus A2 plus A3. We keep going up to AN. All right. So this is our sigma notation. It's a big fancy addition sign. And what we did when we calculated the area there is we figured out the height of our function, height of our first rectangle, times the width of our first rectangle, plus then the height of our second rectangle times the width of our second rectangle, and then the height of our third rectangle and the width of our third rectangle. So each of these were the heights for the corresponding rectangles. And delta x was our width. All right, so how could we rewrite this in sigma notation? So a way to shorten this up, so it's not so repetitive, we could write this as the sum going from I equals 1, and our ending n value here is going to be 3. So essentially there's 3 terms that we're adding together here. So we're going to start our index at 1, and we're going to count up to 3. And what we did is we calculated f of xi. So this was the height of the ith rectangle times delta x. So the way we read this is we do this calculation, and we do it 3 separate times in this case. So we start this calculation at I equals 1, and then we do the second calculation, and then our third calculation, and then we add those results together. So this is how we could write this in sigma notation. And it's this gadget. This gadget is called our Riemann sum. So in general, when we're not just using 3 rectangles, if we wanted to use arbitrary n, how this would look is this would be the sum, again, that's what the sigma means, starting with I equals n, I equals 1, and going up to n, whatever we want n to be. And normally when we're doing these, as we'll see, to get better and better approximations, we normally choose n to be relatively large. So you might do like n equals 100 or n equals 1,000 to get a really good estimate for what the area is. And so the function evaluated at some x value times delta x, if we calculate this and then repeat that n number of times and add the results together, we get our Riemann sum. And looks like got cut off here. There should be a delta x at the end. So when we do this Riemann sum, we call these x values, xi star, we call these sample points. And these are just the places that we're using to get the height for each of our rectangles. And then the width, delta x, We've kind of seen this. It's the length of our interval, and then we're dividing it by n, or dividing it by the number of subintervals we want. All right, so if we go back up to our example, what were the sample points on the rectangles that we did? So for the first rectangle, the x value that we used was right in the middle. So our first subinterval was going from 1 to 3. And to get the height for that first rectangle, we used x equals 2. So x equals 2, we would call this x1 star. So that's our first sample point. So the idea is, once we have our subintervals, we can pick any point that we want in that subinterval, and we can look at the corresponding point on our graph to get the height of our curve. And so normally, the way we do this is there's kind of three natural choices for a subinterval. We could pick the left endpoint, we could pick the right endpoint, or we could pick the midpoint. But you really can pick anything in the middle, anything in there. So in this case, we picked the midpoint. So that was our first sample point. And we plug that in to get the height of our function. And our second sample point, call it x2 star, we used 4. So we used halfway between 3 and 5, the midpoint there. And then for our last subinterval, the sample point that we picked was 6. So we'd say x3 star is equal to 6. All right, so we're going to be practicing more of this in class, but I wanted to just get into this idea of sigma notation and the idea of calculating our Riemann sum. And what we'll see is, well, how do we actually figure out the left endpoints, the right endpoints, and midpoints in general? So it's kind of a systematic way to do that, but we'll get to this in class. So we'll see you then. Bye-bye.